coming out. It's nice to see that there's so many people interested in this subject. I sense that there may be a sea change going on in public attitudes toward climate change, but alumni at MIT have more or less gotten this picture for a long time. I want to preface what I'm going to tell you tonight about the problem of global warming by reminding you that climate science existed for literally hundreds of years before it was recognized there was a problem with climate. And like any other scientific endeavor, if you're scientifically inclined, once you get into it, it's really, really interesting. Okay? And it would exist and be fascinating if we had no problem with the climate at all. And so you have to remember that scientists, I hope I'm one of them, and certainly my students and my colleagues, are motivated the same way that most scientists are motivated by anything. They just want to try to understand the natural world. That's where I'm coming from. But we are thrust into the position of having to try to deal with something which is a looming and possibly a large set of risks that come from climate change. So my aim here tonight is to tell you what I think where science is at in assessing this. But because I spend more and more time talking to people here at MIT especially, but elsewhere, about how we're going to deal with those risks, I like to try, risk is a downer. I don't want to just leave you with that. How are we going to deal with that? And I have to tell you right up front, I'm pretty optimistic. At least on the technological side, where the technology is headed, that we can technically deal with it. We just have to figure out how to deal with it politically. So what I'm going to try to do is give you a brief history of the Earth's climate and climate science, and to present you the evidence that we see that our activities really are having now a pretty strong effect on climate. I wouldn't have said that 30 years ago, but it's pretty clear today. To tell you what we feel are the risks to society from climate change, and to get to the whole problem of solutions and opportunities. But let me say, and this sounds very Machiavellian, I know, but I firmly believe that where there's risk, there's opportunity. And so I've been increasingly interested in what those opportunities are. Okay. So let me begin with this fascinating record from ice cores in Antarctica. Now, one of the great achievements of climate science, and again, this is one of those achievements that's somewhat independent of the problem of climate science, is the field of paleoclimate, which is unraveling the Earth's climate history from the geological record. There's a lot more to this than I have time to tell you about tonight. But this just shows you some of what's going on. So this is a record going back 450,000 years to today. And there are three things on this record. There are two cores, ice cores from Antarctica, which are showing you basically swings in temperature. So there's high temperature here, here, and here. And where we are today at relatively low temperature, you're seeing 4 or 5 glaciations. There have been about 10 or so over the last 3 million years. And you might be wondering, how do we know what the temperature was thousands of years ago, long, of course, before thermometers? That's one of the great achievements. This comes from looking at the ratio of 2 isotopes of oxygen and water molecules locked up in the ice. You might like to know or wonder, how does that tell us anything about temperature? Well, I'll leave you with that puzzle for a minute. It's very interesting. Now, the bottom record is from something completely different. It's looking at, again, an isotopic ratio, but this time it's from the shells of micro-marine organisms that have settled, died, and settled to the bottom of the ocean and got buried. And that, of course, accumulates over time. So you can take a core in the deep ocean. And what that is telling us, and I'll let you puzzle over this, is fairly precisely the volume of ice on the planet. Just think of that. We can figure out what the volume of ice was actually going back 800,000 years now. And you can see this is plotted on a reverse axis, so high is on the bottom, low is on the top. You can see how well that's correlated with these completely independent measurements. So there's no question that the Earth swung in and out of ice ages. They're real, they were big. And if we turn the clock back a mere 20,000 years, which is a blink of an eye geologically, this is a reconstruction of the Laurentide ice sheet over North America, where we're all sitting or standing at the moment. It was under about a mile of ice back then. That's a lot of climate change. And if you could have crawled out from under the ice here in Boston, you could have walked from Boston to Provincetown in a straight line and not gotten your feet wet, because sea level was about 400 feet lower back then because of all the water locked up in the ice. This is a reconstruction of the temperature difference between that time, 20,000 years ago and today. And you can see it was very cold, of course, over the ice sheets in North America, the Scando ice sheet here in Europe, northern Europe, and a little bit cooler in the tropics, but the tropics have always been kind of even over geological history, and I'll come back to that point. The tropics are amazingly stable, not just over ice age cycles, but over even larger climate swings in the distant past. This is the recovery. This is going back 24,000 years. This is today. This is the recovery of sea level again, from paleoproxy data. So it's sea level relative to today's in meters. So 140 meters is roughly 400 feet. That's how much lower it was back then. And you can see that as the ice started to melt and retreat, sea level came up and stabilized about 7,000 years ago. Now, you heard a lot of talk about what dislocation we would face if sea level changed by a meter, which you could hardly see on this map, right? 1 meter. And that's the lesson here. That's the important lesson. People sometimes ask me, you know, how do you know this is the ideal climate? Well, that's a very simple question to answer, and it's obvious. It was about this time that what we call human civilization started to develop, 7,000 years roughly. Of course, the species have been around a lot longer than that, but we were nomadic. And what happened was we built a civilization that's extraordinarily finely tuned to the very remarkably stable climate of the last 7,000 years. So by definition, that climate is optimum for us because we're adapted to it. And if we go either direction, it doesn't matter if we go up or down, it's going to be dislocated. It's not going to be a problem for the planet much, but it will be a problem for us. That's the whole problem we're up against. You can see that kind of climate changes the Earth can have naturally are staggering compared to the kinds of climate changes we're worried about in the future, simply because we're so finely tuned to the current climate. And we pretty much know why the Earth did go in and out of these glacial cycles. It's a remarkable achievement. It dates back actually to the 19th century, but a big step was taken forward by this Serbian mathematician, actually, Milankovitch, who understood that the Earth's orbit around the sun and the rotation about its own axis have perfectly periodic, perfectly predictable oscillations. Right? And that's mostly due to the gravitational influence of the moon and other planets. Those oscillations have this character. The degree of helicity of the orbit, or eccentricity of the orbit, changes over about a 100,000 year period. The obliquity of the Earth's axis, its angle with respect to the plane of the rotation of the Earth about the sun, 23.5 degrees today, that changes, that oscillates in about a 41,000 year period. And the equinoxes precess like a top. Okay, the Earth's rotation precesses, all of which, none of which I should say, really affects the total amount of sunlight intercepted by the Earth, but which does affect rather profoundly its distribution and latitude. And that turns out to be very important. So here's how we know that Milankovitch, by the way, of course, Milankovitch was ridiculed in his own time. How could this possibly be? Of course, people who discovered that there were ice ages were also ridiculed. That this seems to be the fate of climate science. Now, this is a chart going back 1 million years. So this is time in thousands of years. So that's a million years. And there are two quantities graphed on here. The red curve is the amount of sunlight intercepted by the high northern latitudes, the high Arctic, from the Milankovitch mathematics, which are very well known. You can see these oscillations reflecting the orbital variations. The black curve is the time rate of change, the ratio of 2 isotopes of oxygen in deep sea sediments. You couldn't ask for 2 more completely independent measurements, right? One's actually not a measurement, it's a calculation. And you can see how well aligned they are. The interpretation of this is the rate of change of the ice volume on the planet, and it's high when there's not much radiation coming into northern latitudes and so forth. So this is an elegant proof of the Milankovitch hypothesis. Do we know everything there is to know about that ice cycle? No. But we know the basic cause of it. Right? And that's a big leg up, and it's a fantastic accomplishment of geochemistry and paleoclimate. Now, I want to turn to a little bit of the history of the science and go back to John Tyndall, a very gifted Irish polymath. He looks pretty grim, doesn't he? I'm not sure. He built this apparatus, which you can go see today. If you're in London, you can go to the British Museum, it's there. And by his time, it was understood that the Earth's atmosphere somehow played a role in keeping the Earth warmer than it would otherwise be. It was pretty well understood already by then. But it wasn't understood why. It had something to do with gases in the atmosphere. So he set about empirically determining which gases were doing it, so he built this apparatus as a long tube. He could fill it with gases of his choosing, like nitrogen or oxygen, then shine a light through it from here, and then measure how much of that light got absorbed as a function of the wavelength of the light. It included infrared and ultraviolet and all this stuff. It's a very laborious set of experiments to do. And what he discovered surprised him greatly. We'll come back to that in a minute. And the scientists of the time. It was a big surprise. What they were after was trying to understand this effect. And we now call that the greenhouse effect. And I'm going to give you a 1-minute tutorial. First of all, I have to tell you it has absolutely nothing to do with greenhouses. It's actually a very poor metaphor, but we're stuck with it. So if we didn't have any greenhouse gases in the atmosphere, it would be a very simple picture globally. Certainly when sunlight come in, some of it would be reflected, the rest of it absorbed, and for the surface not to heat up or cool off, it would have to radiate infrared radiation at a rate sufficient to balance this absorbed sunlight. That rate goes up as the fourth power of the temperature. And so it's very straightforward to calculate how hot the surface had to be. And it's about minus 18 degrees C. Very much colder than what we observe. If that were the case, we wouldn't be around to talk about this. Right? So the greenhouse gases basically are absorbing some of this infrared radiation coming up from the surface and re-radiating that, so they remain in balance. They're re-radiating that both down and up. And so if you're at the surface, you have to be warm enough not just to balance the incoming sunlight, but to balance the back radiation from the atmosphere, also the clouds in the atmosphere, which aren't on this cartoon. It's a really fantastic thing that we get, on average, around the planet, over a year, twice as much energy in the form of radiation from the atmosphere as we do directly from the sun. That's how powerful our greenhouse effect is. Twice as much. And that means our surface temperature is 15 degrees and not minus 18 degrees. So that, again, was understood actually before Tyndall. But Tyndall was surprised as he did the same thing most of us would do if we were empiricists. We'd start with the most important gases in the atmosphere, molecular oxygen and nitrogen. Together with argon, they comprise more than 99% of the mass of the atmosphere. He put them in his tube, he measured the absorption, and he got zip. Nothing, right? Essentially nothing. Now today we know there's a little tiny bit, but it isn't really very important. So he was puzzled and he started to put other gases in his apparatus. Water vapor, carbon dioxide, nitrous oxide. He discovered that in contrast to the main constituents, these were heavily absorbing in the infrared. And he was quite surprised and did detailed measurements to find out how much of the radiation. And it turns out that these gases and a handful of other trace gases we discovered since then make the lower atmosphere almost opaque to infrared radiation. Although still transparent solar radiation, none of these gases, except maybe a little bit of water vapor, absorb heavily in the solar part of the spectrum. So those gases, which make up on average less than 1% of the atmosphere, make the difference between a surface temperature of 0 degrees Fahrenheit and 60 degrees Fahrenheit. Okay? Now, just to show you the proportions here, this is a pie chart showing the proportions: nitrogen, oxygen, argon, which doesn't do anything, is green. The greenhouse gases are the orange sliver. I hope you could see that. I suspect you can't if you're in that. That's okay. It's a very thin slice. And that slice, that orange slice, is what makes the difference between 0 and 60 degrees. Now that sounds counterintuitive. Why should such a tiny fraction of the atmosphere do that? We do have experiences like that. A little, if you live in an old house and you haven't had your heating upgraded, a little tiny bead of mercury in a thermostat is what's controlling the temperature in your house. All right? It's not the source of energy, obviously, but it's the control. In some sense, these greenhouse gases are a thermostat, and over geological time, the concentration of those greenhouse gases is strongly regulated by the Earth system, which is why we have a climate that never completely ran away into a runaway greenhouse like Venus or an ice-covered snowball. So water vapor, but it's actually more surprising even than what I've told you, because the most important greenhouse gas, just because it dominates the mass of the greenhouse gases, is water vapor. It's about 0.25%, but as you know perfectly well, it's highly variable in space and time. And its residence time in the atmosphere is only about 2 weeks. So if I blew up an enormous water balloon and doubled the water vapor concentration, it wouldn't affect climate, because 2 weeks later it would all be back in the ocean. All right? Its concentration is controlled by temperature. And so it's a feedback. If you cool the temperature, there'll be less water vapor, and that will allow more radiation to go to space, and that will amplify the cooling, ditto the warming. And that's a very important feedback in the climate system. So we're left with the interesting idea that climate is strongly influenced, in some ways controlled, by greenhouse gases that are long-lived, like CO2, many thousands of years, whose concentration amounts to about 0.04% of the atmosphere. That's our thermostat. Okay? That's why it's not very hard for us, unfortunately, to change that number, because we're dealing with a pretty small amount of it to start with. And its concentration, as I'll show you, is increased. I have to keep changing this number, but I did update it yesterday, 46%. Since the dawn of the Industrial Revolution. So, this is for the quantum physicists. How many quantum physicists are there in the audience? How many people take? Oh, there's one or two. Okay. Why is this so? Because the greenhouse gases have more complex molecular structure. They have more degrees of freedom in interacting with radiation. So water vapor is a bent triatomic molecule, has a permanent dipole moment, pure rotational bands, and rotation vibration transitions. Ozone, which is active in the stratosphere, is like water in that respect, and it's also involved in photodissociation. And carbon dioxide doesn't have a permanent dipole moment, but it does so. It doesn't have any pure rotational transitions, but it does have temporary dipoles during vibration. So it's all quantum physics. Now, Tyndall didn't understand that, and that came later, but he did measure it, and that was the important thing. And there are other gases like nitrous oxide and methane that are important as well. So when we come down to it, this is a spectrum showing the energy coming down per unit wavelength from the sun. This is the Planck curve here. And going out from the Earth. These are the long wavelengths, these are the short wavelengths. And this shading shows how much of the sunlight in the absence of clouds at these various wavelengths gets down to the surface. And this blue shows how much is going back out to space. So you see on the solar part of the spectrum, it's in the UV. A lot of it gets absorbed, and that's by ozone. If you look down here, you can see it's ozone that's doing this absorption. And it's a good thing for us, because we can try if that were true. And if it's not cloudy, most of the sunlight gets through. There's some absorption bands, mostly in water vapor here. On the other hand, the radiation trying to get out has to get out through this narrow window. The rest of it is absorbed and re-radiated by water vapor, carbon dioxide, and other greenhouse gases. So that's about as nerdy as my talk is going to get. You might be relieved to hear it, or maybe not. I don't know. So we start off with the simplest conceivable climate state. It's one-dimensional. We only worry about how things vary with altitude. And what we noticed right away, and this is a long time ago, is that this state of radiative equilibrium, where every sample of gas is radiating as much energy as it's absorbing, is horribly unstable in convection. And so atmospheric convection is the main agent for transport, besides radiation, for transporting heat and water in the vertical. And the latent heat of when water condenses is a very large number, plays an important role in the atmosphere. But convection is very fast compared to radiation. And convection is important because it takes water from its source at the surface and lofts it into the troposphere. Otherwise, the troposphere will be dry. So this is the real challenge in climate science. This is the source of most of the uncertainty and why we can't give very definite answers to things. This is a marvelous photograph from the International Space Station showing this whole spectrum of cumulus clouds. That's what I mean by convection. From tiny little clouds down here that don't rain to tall cumulonimbus clouds that go all the way up to the tropopause here. And these ice anvils are thin and in an absolute sense contain very little water, but they have enormous effects, both on reflecting sunlight and on absorbing and re-radiating infrared radiation. So we have to deal with this soup, and we have to understand that, and that's a big and fascinating challenge in climate science. And it's water in all of its phases that gives us the headache. I think I'm going to skip that chart. This one shows you what you're up against. So this is a profile in the state of radiant equilibrium of the relative humidity. So 80% at the surface, and then it starts to tail off with altitude. It reaches a minimum. This is pressure. This might be 6 or 7 kilometers above the surface. And then this is the level of the anvil clouds where it gets close to 100%. Now, if we go into the way that convection is represented in this model, and we start fooling around with parameters that deal with how efficiently cloud droplets collide and form rain droplets, and these are called microphysical processes, and believe me, most of my climate science colleagues wish that they didn't exist. And they don't typically know much about it, and then the cloud physics community is not very interested in climate, so there's this academic stuff about it. If you change those parameters, if you make precipitation much less efficient, if the atmosphere gets incredibly humid, that's a whole lot of greenhouse gas you're putting in. On the other hand, if you make it super efficient, the atmosphere dries out. So what I'm telling you is that the Earth's climate is, among other things, exquisitely sensitive to very complex processes happening on microscales inside clouds that deal, for example, with how much water gets converted into rainfall, or how much of that re-evaporates, how much gets put into ice clouds. You can see what we're up against, all right? It's a very interesting problem. Now, in the recent years, we've been able to simulate these states with computationally, and we do this in boxes. This box is 1,500 by 500 kilometers in dimensions. And we run the state. Radiation is cooling the atmosphere, convection is heating it and lofting water. And if I played you a movie, which I don't dare do because I have bad luck on it, it would look like boiling water and you'd all go to sleep pretty soon. All right? It's great. It's better than a lava lamp. But this is a snapshot, okay, showing the column integrated water vapor, in this case, the surface precipitation. If you can see it, these little dots are individual rain shafts. And then this is showing you the amount of long-wave radiation going in space. Where you see blue, there isn't much. That's the blocking by the anvil clouds. And this is highly time-dependent. And when we first started to run these, we saw pretty much what we thought we were going to see. Boiling water, kind of. It's all random, it's chaotic. Okay. Then we were in for a big surprise. And this happened not very long ago. You run that model a bit longer, and now this is what you have. Does it look anything like what I just showed you? No. All of the water vapor, all of the rainfall is concentrated in a blob. And there's nothing going on outside of it. And the first time that my colleagues saw that, I didn't do this, they said, oh, there's something wrong with the model. They went back and they tried to tamper with it and fix it. And they couldn't. And then other people with completely different models started seeing the same thing. See, climate science is still full of surprises. This is the outgoing long-wave radiation. It's now also blocked, but in a small patch like this. And we've done lots and lots of work on this. It's called self-aggregation. If you do it on a rotating planet, it aggregates into hurricanes. Okay, this is a box just like the other one, but it's a rotating box. And those are basically a measure of how much water is in the column, and you get these nice hurricanes. And I think some of you may think that that reminds you of something you've seen before. And I thought, yeah, that's Van Gogh. And then somebody told me that it's true that Van Gogh turns out to have painted the first known portrait of a climate scientist. Now, the thing about the self-aggregation is that it profoundly dries the atmosphere. Although it's not very dry in this clump, on average, it's much drier. So this is a vertical profile of humidity before the aggregation takes place. And this is a profile of humidity after. You've lost this huge chunk of greenhouse gas. Now that's very interesting because the aggregation itself turns out to depend on temperature. The warmer it is, the more likely it is to aggregate. But if it aggregates, you lose all the greenhouse gas and the system will cool off. So we've kind of tripped on a kind of thermostat for the tropics, and it works in models. So this is a simulation. Now you're looking at time. You're looking at ocean temperature in a simulation where we did not permit aggregation to occur by making the magnitude small, and the temperature just keeps rising over time. And in this simulation, it's exactly the same, but we allowed aggregation, and it hits this threshold and levels off. So this is one of many examples of a fascinating surprise in climate science. And we're still trying to struggle to understand what it really means for the climate system. I think it has a lot to do with the stability that we've observed over all geological timescales of the tropical atmosphere. It doesn't work outside the tropics, but boy, is it a stabilizer inside the tropics. This is just a mosaic of satellite pictures of water vapor in the atmosphere to remind you it's very complex. This distribution has got variability in all scales, and of course it's time dependent. So water in all three of its phases is the greatest source of uncertainty in understanding and modeling climate, but it doesn't stop us from doing certain things successfully. So I'm now going to turn back to history and show you some results of a Swedish chemist, Nobel Prize-winning chemist who lived at the end of the 19th and early 20th century, Svante Arrhenius. If you've been to Sweden, you will have come across his name, no doubt. And he looks even less happy than John Tyndall. He's a climate scientist. They look so unhappy. Look at that. But, he said in 1906 that he was the first to start to worry about the fact that burning fossil fuels would do something to the carbon dioxide content. And he was a serious chemist. He understood a lot about the system. He did a calculation. If you double carbon dioxide, you raise the surface temperature by 4 degrees centigrade. Now compare that to the most contemporary estimate from the IPCC of between 2 and 4.5 degrees. This was obviously with pencil and paper, clever measurements of moonlight, literally. He came at this back of the envelope estimate. It's within the range of modern estimates. So I would say that in terms of global mean temperature, all modern climate science has been able to do is to put error bars on his estimate. But of course, we hope we've done a little bit more than that. Was Arrhenius right? Well, I would say the data is fairly persuasive on that. So what you see on this curve in blue is a measure of carbon dioxide content, actually the logarithm of it, going back to Arrhenius' time. And the red curve is annual mean, global mean surface temperature, which is fairly robustly measured out back to about then, not much before then. And of course, there are all kinds of random variability and other kinds of force variability, like volcanoes, changes in sunlight. But by and large, the temperature has followed the Arrhenius prediction. Arrhenius predicted what would happen, and he did it 100 years ago, more than 100 years ago. Climate science is not new. This was not a big surprise to people who work in climate science, right? This is not something that's happened in the last 20 years in climate science. Carbon dioxide, we have very good records of that from bubbles of gas trapped in ice cores, and we've been measuring it since 1958. This is a record going back 1,000 years to 1000 AD. These are various proxies, very stable at 280 parts per million. And then in the dawn of the Industrial Revolution, it's done this, okay? And it's at 410 today, so it's up here somewhere. We did that. Nobody in my field doubts that. There's 100%, essentially 100% certainty about why that happened. It really isn't any doubt. Of course, we can go further in time. This is a record of temperature in the Arctic from paleoproxies, a bunch of different ones. That's what gives rise to the shading. It's a scatter among different proxies, going back 2,000 years to 1 AD. And you can see the slow decline, which is consistent with the Milankovitch cycles. And that went on for another 10,000 years. We plummeted into another ice age, roughly 10,000 years. But what happened at the end of the series was, again, the Industrial Revolution. About this time, it really turned up. The red curve is instrumental measurements of temperature, consistent with the paleoproxies. So we have lots and lots and lots of evidence that we're changing the climate. People think that what we know comes from global models, global climate models, which are big, hopelessly complicated models. And a lot of people think that's the only basis for understanding, and that's completely wrong. We understood this before there were models like this. They have helped us in some respects. But if it's all that climate science were based on, I wouldn't be in climate science, all right? That would be unattacked. But the models are useful. And some models are useful. This is an attempt to replicate global mean temperature in black from about 1890 to 2000. The black is, again, from thermometers. And the red, with some scatter, is from attempts to replicate that with global climate models subjected to the same variations of sunlight, greenhouse gases, and volcanic aerosols as nature apparently was. And it does, if you look at the red curve, a fairly good job. But if you leave out the anthropogenic effects, you really can't get this upswing at the end of the record. And there's nothing you can do to do that. And that's another piece of evidence that we're responsible for that. So, if you do a poll of climate scientists, it has been done, and roughly 97% will say, yes, this is real, it's man-made. That's not argued in science. It's argued out in politics, as you know. It's not argued in science. There are arguments in science, but not about that. 97% is pretty good. I don't think you can get 97% of biologists to say they agree with Darwin. Maybe it's 96%, I don't know. So what are the risks? Well, some of them you're very familiar with. Increasing sea level. We're very highly adapted here in Boston. As you may know from reading the newspaper, if the sea level went up a foot or two, there'd be an awful lot of adaptation. But the thing that keeps us awake at night are hydrological events. Floods, droughts, because of their effect on the water supply and food supply. And it's a very simple piece of climate physics. You don't need computers to tell you this. As you warm the climate, hydrological extremes get basically the hydrological cycle becomes much more volatile, which means you get more downs, droughts, and ups, floods. So I work on hurricanes. We predicted more than 30 years ago that we'd see an increasing incidence of high category hurricanes, and if you can pay attention to the news, that's happening. More heat stress, of course, another health risk. And then this is the big one. It's armed conflict. And it's not, obviously, a direct effect of climate change. It arises from political instability that's catalyzed by food and water shortages that are brought about by climate. Arguably, this is already happening in places like the Middle East, northern Africa, and so forth. There are benefits of climate change that have to be weighed into the calculation. There is some increase in plant productivity when you put CO2 in the atmosphere. And of course, you expect to see a reduction in health problems related to cold weather. Something you're all dear to your hearts right at the moment. But if you weigh all of this, and this is again just a question of us being extremely well adapted to the climate that we enjoyed for 7,000 years, that's all it is really. If you move away from that, it causes problems. And our own Defense Department is extremely serious about this. They rate that as very high on their list of national security threats because climate, when you read it for yourself, what they say, climate change contributes to political destabilization, puts enormous pressures on immigration, weakening of fragile governments. Does that sound familiar? And so forth. So if you go talk to people in our Defense Department, they're dead serious about climate change, and I'm not kidding about that. So scientifically, as I've said before, the sources of uncertainty are things like clouds, which are really tough. Water vapor, I haven't talked about the ocean, but we don't fully understand the role of the ocean in climate. And aerosols, man-made aerosols from burning land and fossil fuels tend, on the average, to cool the climate. And they did so rather profoundly for a short time at the end of the 20th century, for example, in the northern hemisphere. When we put it all together, as scientists, we think in terms of probability distribution. So this is not to be taken quantitatively all that seriously, but this is a probability of experiencing a particular global surface temperature change from doubling carbon dioxide in the atmosphere. And so 90% of the probability curve lies in between about 1 3/4 of a degree and maybe 4.5 degrees. And then you have these tails of relatively low response and a relatively high response. So the problem for society is the most probable outcome, 2 to 3 degrees, will be dislocating, expensive, and to some extent deadly, but probably not existential. If we are lucky enough to wind up here, it's not going to be much of a problem. If we're so unfortunate as to come out here, that is existential by all reckoning. That's very, very, very serious. Is it a big event? Is it a big probability? No, but if I told you it was 5%, would you let your daughter cross a busy highway? If I told you there was a 5% probability she'd be run over and die? Probably not. Whenever we assess risk, we have to convolve the event probability with the cost of the outcome. And that cost, I don't have it on here, just goes up really, really fast here. And when you put those curves together, then you have something like a true measure of risk. But we're on track to do much more than doubling carbon dioxide. That is, that tail is going to be more like 20%. The reason is that we're not doing anything about it. So these are projections of carbon concentration out to 2100. This is the doubling of the pre-industrial value of this curve here. We're going to cross that at about mid-century. And all these different curves depend upon various levels. What we do is business as usual, and economies don't collapse. We'll more than triple CO2 by the end of the century. That's not that far off if you're thinking about grandchildren, for example. And the problem is, once you put CO2 in the atmosphere, this is time, this is projected CO2, these curves assume that you're shutting off the space when the CO2 reaches a certain concentration. When you do, you get a gratifying rapid decline, or rapid, a couple hundred years, all right? But then a much slower tail off. It takes the natural system a long time by human standards, not by geological standards, to get rid of it. This is the associated temperature change. Basically, the message is whatever temperature you have when you shut off the CO2 is what you're going to be stuck with for many thousands of years. So unless we can pull CO2 artificially out of the atmosphere, we don't have much time to act. So now let me try to change to something a little bit more upbeat here. What can be done about it? Well, you've heard most of this. I'll go through it quickly. There are renewables, solar and wind. The price of these things is falling very rapidly, but they have drawbacks. Most energy experts say that barring a breakthrough in storage, globally you're not going to get up to more than 30% because of the intermittency problems. And it's limited by the intermittency and, of course, lack of storage. People are working on that. There's reason to be hopeful. But right now, you can't bet on that being a 100% solution, in spite of what you might have heard. There's carbon capture and sequestration. We can do that. We are doing it experimentally. It's just too expensive right now. And there's some hope that with technical improvements and scaling things up, that the price might drop, and that's being worked on, and it should be worked on. I would add about $1 million per ton of CO2 to the price of fuel, and economists would tell you that's probably not going to fly. If you beat it down to $50 a ton, then you can start talking to economists about it at least. But right at the moment, we don't have much incentive to develop that, and I'll get back to that in a second. And then there's nuclear fission and fusion, and I want to talk a little bit more about that. This is the positive message, and it's not so much about nuclear power. I'm a big fan of nuclear power and unapologetic for it. If you want to come and attack me, do it. All right? I'm ready. It's the safest form of energy, by far, we've ever had per kilowatt hour generated. No question of that. I'll show you that chart. But this is the thing, from a carbon climate scientist perspective, this is showing an 11-year period during which various countries most rapidly increased their energy capacity, carbon-free energy, in kilowatt hours or megawatt hours per year per person. And so there were 3 major countries that essentially completely decarbonized: France, Belgium, and Sweden. So what I'm telling you is not disputable. 3 countries have decarbonized their electricity. Not tomorrow, but yesterday, okay? So we know it can be done. It can be done if there's the will. They didn't do it for climate reasons. They did it for national energy security reasons, but they did it. And they did it mostly with nuclear. Germany, down here, spent a fortune on solar and wind. That's their curve, all right? And they have the most expensive power in Europe at the moment. And they have reached an intermittency wall where the surrounding grid, the European countries, are after them not to increase their renewables because they can't handle volatility in the grid. Now some of those technical problems can be addressed, but right now they're not being addressed. All right? So Germany says they're off nuclear. Their carbon footprint didn't go down at all. They're burning just as much coal as they were doing it before this revolution. So they replaced their, instead of replacing coal with solar, when they replaced their nuclear. I'm sorry, that was dumb. If you're German, you can come and give me that. It's a very dumb thing to do, frankly. And I think most energy people, they won't tell that to you quite as frankly as I have, but it really was. It did not help the climate system at all. This is a really upbeat graph. It's mortality by energy source. It's the number of deaths per trillion kilowatt hours generated, right? By source. King coal is over here. It's very lethal. 13,000 Americans per year die of coal-related diseases, according to the American Medical Association. 13,000. Now, if I said 1,300 people died from nuclear power, it would be shut off tomorrow. In fact, the number is 0 in the United States, as I'm sure you're aware. Okay. Oil is next on the list. Biofuel, coal, gas, hydro, solar, and there's nuclear, and that includes the only serious accident in terms of mortality we've had is Chernobyl, a design that should never have been built in the first place. You know, wings used to fall off of airliners in the 1950s. We didn't quit flying. We found out what went wrong and we fixed it. Okay, but we can do better. So there's a lot of work going on. I'm going to skip over this quickly. It's called Generation 4 fission. Reactors are passively safe. They can help process waste from the older generation reactors. They operate at ambient pressure and very hot temperature. They run on other kinds of fuels and have long plant lifetimes. And then we have a very upbeat project at MIT. You might be aware of it. If you're not, I encourage you to find out about it. It's the Spark Fusion Project. Technical breakthroughs in magnets have made those people very optimistic on about a 15-year time scale of commercializing fusion. And then we're really going to be in good shape if we can get to that. All right, so you don't have to believe me on nuclear. You can argue with me. But I would say the argument is probably immaterial to society. I'm a strong proponent of letting the markets figure out what the best solutions are. So how to catalyze a solution? You price the negative externalities of carbon emissions. It's simple. It's a bedrock free market principle right out of Milton Friedman's textbook. This is not Green New Deal. This is conservative politics. I'm not necessarily endorsing them across the board. But if you're so inclined, we're not being radical about this. It's a very established principle. 95%, I'm told by Marty Weitzman at Harvard, more than 95% of U.S. economists support this. I'm not one, obviously, I'm not an economist. If we did this, coal would vanish almost instantly simply because of health externalities. Markets, rather than ideologies, would determine the best mix of solutions. So we don't have to argue about solar versus wind versus carbon capture versus nuclear. Society and markets would figure that one out. So let me summarize. Several aspects of our science are well established. It's not like we know nothing. And climate science dates well back into the 19th century. It's pretty well established. The Earth's greenhouse effect triples the amount of radiation absorbed by the surface. But it's regulated by trace gases that comprise no more than about 0.04 of 1% of the mass of the atmosphere. But the concentration of these has increased by about 45%. Beginning with Arrhenius, simple models predict that increase in global mean surface temperature to around 3 degrees for doubling, plus or minus 1.5 degrees. And these are consistent with results of global climate models. But I believe the theory more than the models. Long atmospheric lifetime of CO2 does limit the window of time in which we can curtail risks unless we can figure out how to extract the carbon. Renewables are fine, but if you want to decarbonize fast, we know how to do it because it's been done. Right? There's no doubt about that. Climate risks, if you think nuclear is risky, I think you're wrong, but if you think it's risky, I would argue at any rate, climate risks are much, much, much larger than nuclear risks. I'm not talking about weapons, obviously, just power. We're going to have to do this anyway. Why shouldn't we start now? Because we're going to run out of carbon-based fuels sooner or later. The real world, 20 years from now, the question is, are we going to be selling clean energy to China or buying it from them? That's what it really boils down to for the US. And the way you achieve rapid decarbonization, according to the economists, and I have no reason to doubt them, you eliminate energy subsidies, you stop playing favorites, ideological favorites. You tax externalities, negative externalities of health and carbon, and let innovation take over. You might think about how to structure such a tax, of course. And the other thing governments can do very effectively, because it doesn't cost very much, is to fund research on the development of low carbon energy and carbon extraction. So I'll leave you with those thoughts. Of course, I'm happy to answer questions. Anyway, let her rip. Yes?
So, obviously, it's pretty essential to the whole picture that it's human activity that's creating this increase in CO2. And let's just accept for the moment, as I do, excellent lecture, the prediction of the Swedish scientists has been confirmed by the global climate models. But there's this kind of meme out on the internet that the natural sources of CO2 far exceed human sources. Is that incorrect? Because,
yeah, it's radically incorrect. So volcanic emissions are about 1% of current human emissions. But don't get me wrong, on geological timescales, it's a part of the carbon cycle, the emissions of carbon dioxide from volcanoes. Carbon gets buried. Biology takes carbon out of the ocean, buries it on the seafloor, and a certain rate gets subducted in trenches, and then ultimately, we're talking about geological time, long geological time scales, comes back up in the atmosphere. that's actually a measure of how strong our effect is, that we're overwhelming that cycle by a factor of 100.
Yeah, thanks for an excellent lecture. Over the past millennium, we've had extended periods of both warming and cooling of the Earth. The warming of Greenland around the 900s, then the little ice age around 1675. And they were both for extended periods. Can you comment on any speculation what might be causing those cycles?
Yeah, you know, this is a sort of fascinating thing that keeps climate science going, even if we didn't have a problem with climate. So there was this little ice age, for example, in Europe, and at least in Europe. Well, part of the problem is that thermometers were very isolated back into Europe, and paleoproxies. Anyway, it's not clear how global that was, but it was enough. You know, it was about a half a degree or a degree of cooling in Europe, and it was enough to cause havoc. What happened? Well, one thing we know is that the people who studied sunspots through telescopes, beginning with Galileo, started to look at them in 1609, and the Scandinavians made detailed records of aurora borealis. Sometime in the middle of the 17th century, the auroras went away, and the sunspots went away. It's called the Maunder minimum. And solar physicists believe that that little ice age was partially caused by a slight diminution, a natural diminution of sunlight. But there was a lot of volcanism going on at the same time. The bottom line is, make no mistake about it, there are natural variations in the climate. And that 7,000 years of stability, that graph I showed you wasn't wrong. The things you're talking about are tiny blips on that. And even those tiny blips cause problems for humanity even back then. Are you going to, yeah.
What changed 7,000 years ago that resulted in the sort of regular major oscillations dampening out and going to stability?
I probably accidentally tricked you by switching time scales. So those regular oscillations were on a graph that was 450,000 years long. That 7,000 years is part of the graph that was 45,000 years long. So what you saw is coming out of the latest oscillation. And you know, if we weren't around, right, 10, 15,000 years from now, something like that, we would go back down.
What causes the large oscillations over the long time scale?
Pretty surely the Milankovitch cycles, the orbital variations. So I'm going to ask you to pick the questioners because I can't see them.
Yeah. Oh boy, I think, yeah.
Thank you. Excellent presentation today. Could you give us your opinion on abrupt climate change?
Oh, that's an excellent question. This is, together with the armed conflict problem, is what keeps climate scientists awake at night. So, abrupt climate change, or tipping points, it's sometimes called. Unquestionably, these things have happened in the history of the Earth's climate. Going back, 40 or 50,000 years, in the middle of this cold period, there were abrupt warmings that lasted for a short period of time, which we don't really understand. And we're trying to grapple with that. And we live in mortal fear of our own ignorance because we don't understand past abrupt change. We're in no position to rule out future abrupt change. And yet the projections I've been talking about tonight don't account for that. They're therefore quite conservative. But just 2 weeks ago, a paper came out from a colleague of mine at Caltech that showed that if you put enough CO2 in the atmosphere, like 1,000 ppm, all of a sudden the subtropical stratocumulus clouds disappear, and they're responsible for reflecting a big chunk of the sunlight absorbed by the Earth, so the temperature goes up 10 degrees. Is that established? By no means. Is it plausible? Yes, given the physics that we're describing in that paper. We have to get on top of that, so it's an important question.
Thank you for your talk. A question, how to achieve rapid decarbonization
A lot of that is political.
Yes.
Can you speak to geoengineering? If we can't solve our problem, I mean, politically, we seem to have to get into an emergency before we take action. So what can we do in that situation?
Well, I'm glad you asked that question too, actually. It shows you how much you have to leave out of the talk. As a matter of fact, I'm a co-author of a paper that just came out on Monday, yesterday, on this subject. So, geoengineering is a spectrum of different techniques for deliberately cooling the climate back down, essentially. The most interesting and cheapest of those is called solar radiation management, fancy word, for artificially putting a lot of sulfur into the stratosphere, which is what volcanoes naturally do, and they do naturally cool the climate when they occur. And we've done lots of calculations to show what would happen. The problem is that you're taking an inherently long wave effect with greenhouse gases and trying to compensate with the other part of the spectrum. And it can never be a zero-sum game. You can bring the temperature back to what it was before, but then the rainfall globally will be considerably less than it was before, and that's problematic. Our paper said, what if you bring it halfway back, like a compromise, try to cost that out. We talked a few years ago here at the MIT to the Dalai Lama about this problem. And his response is, you should start doing this right away. It surprised us. It's a classic example of what philosophers call the trolley problem. You know, the trolley is coming down the track, it's running away, you happen to be standing by the switch, you can throw the switch, the trolley will go off on the side track and run over somebody. But if you don't throw the switch, it'll run over 5 people. So do you throw the switch? That's the philosopher's problem. The reason it's interesting is because we attach different morality to a positive action, throwing that switch, than to a positive non-action, or negative, not doing anything at all. So for example, the law probably wouldn't prosecute you for not throwing the switch, and you might go to jail for throwing the switch. And that, in a nutshell, is the problem. You throw the geoengineering switch, you probably are going to end up saving lives, but nobody will ever be able to prove it. Okay? Or if you don't do anything, you're quote-unquote innocent. Although not by my reckoning. Some people. That's the problem.
At the beginning, you mentioned plants as one of the things that would benefit from increased CO2. Could you say a little bit more about that? How big that effect is, and also whether plants can absorb a significant amount of CO2 if we grow grass everywhere?
So plants are a really essential part of the long-term climate cycle, where they take up carbon. But they're not the only things. There are physical processes that do that too. Most of the carbon goes back in the atmosphere when the plants die. And it's more the biology of the ocean that's important in terms of carrying carbon. In greenhouses, if you pump CO2 in greenhouses, plants use carbon and they grow faster. But what happens in nature is then they get up against a different kind of limit, which is nutrients. And so this is not a completely settled issue, but this business about plants doing better only works up to a certain concentration, and to try to go above that, they become limited by other factors in the environment. You know, the trees losing their leaves in the winter, in the fall, and regaining in the spring causes a detectable oscillation in the concentration of global CO2, and particularly in the northern hemisphere, across the peninsula. But the problem is keeping the carbon from going back into the atmosphere.
Turn it into coal.
Right. You can figure out how to do that and burn it in coal and not let companies take it back out.
Hi, I'm over here. Thanks for that great lecture, and unfortunately I've got a lot of questions, so I'll try to do them really quick. So the 0.04% in the atmosphere, if it doubles, what and by what mechanism is reduced so that it all adds up to 100? That's my first question. The second one is, if you, where are we on that elliptical pattern of the, Earth going around? Does that mean we're heading for warmer temperatures, or are we going to a lower? And the last one I have is, in the climate change models, and I'm glad you have some degree of skepticism, but my curiosity is, what do those models, what are the parameters on those models relative to the actual values that we're reading? And should the models be updated and adjusted? And maybe it should be, maybe it wouldn't make it worse or better, but I'm just curious about what those models show.
Well, to take your first point, 0.04%, if you double that, one side effect is you increase water vapor a lot. So, yes, I mean, in terms of percentage, the other percentages have to fall, but of course the mass isn't falling, right? Just the percentage is falling. The second question is, where are we in the whole orbital thing? We're coming off of a peak in northern high latitude radiation that occurred 6,000 years ago, when the Sahara Desert was green, by the way. It's an interesting thing. And we're slowly sliding down toward another glacial cliff in 10 to 15,000 years. But remember, it's a very different time scale. The models are constantly being improved or changed anyway, and there are roughly 20 globally that are quasi-independent, not completely independent, there are some of the same parts. It's a very interesting enterprise, but it's really a way of filling in details. The big picture just comes from the physics that Arrhenius knew about.
Where would I find those models if I would try to look them up and look at the parameters? Is it possible to find them, or somebody's got them?
Absolutely. You can find the models themselves have to be run on supercomputers, but you can find the model output. It's all there. You have to register, but it's free. And you can go. There's an archive maintained by Lawrence Livermore Laboratory, for example, all the model output from the last IPCC.
But I'm more curious about the input, what the assumptions are in the model to create the output.
Okay. Well, if you write me, I can direct you to literature. Yeah.